So today topic is molecular spectroscopy. First we talk about the IR spectroscopy. So we know that for IR spectroscopy, if a molecule, AB molecule, whether it is AB2 molecule, if you want to say whether it is IR active or not, the condition what we need to have, that is the change in the dipole moment, right? So this is the condition for IR spectroscopy. So we have a CO2 molecule. So this question asked many times. So CO2 molecules are having two IR active modes, and these two are one asymmetric and two bendings. So these two bending vibrations are degenerate, so that's why we count it as a two IR active vibrations, one IR inactive vibration, that is symmetric vibration. Okay, so this we know very well about it. So now the frequency nu bar, this we calculate by using the formula 1 by 2 pi root k by nu in hertz. Okay, so this is the formula which we use to calculate the frequency. Okay, now we know that nu equals to m1 m2 by m1 plus m2. So this formula is very important. So on this problem, on this formula only the questions will come. So we'll solve some of the previous CSR questions which are asked in exams. Okay, so here k equals to force constant. So from this formula we can see that the frequency is directly proportional to the force constant, and the frequency is inversely proportional to the reduced mass. So these are the two conditions we have to remember. So now, so what is the we have okay, so we have two examples, CF and CCl. So which one will be having a higher frequency? So here we can see that the frequency is inversely proportional to the reduced mass, and here CCl mass is greater than the CF mass, and that's why CF frequency is greater than CCl. And also here this bond is more polar, and this is the less polar. So this is important one. So if the bond is more polar, the change in dipole moment is greater than 0. Okay, this also we have to remember, because CF, so here the electronegative difference is more compared to the CCl. So because of that, this is having more intensity. And we have two molecules, PO bond and CO bond. So which one will be having higher frequency? So obviously frequency of PO is greater than frequency of CO, because so the oxygen is the second highest electronegative atom in the periodic table, and the carbon is having comparatively, imagine that oxygen is having around 3.5, the carbon will be around 2.2 to 2.5, it will be there. But the difference from the phosphorus to oxygen will be more. So where the difference in electronegativity is more, that is a more polar, and that will be having a more change in the dipole moment. Because of that, the frequency of that particular bond will be greater. CO, nu CN, nu CH, nu HH, then we have nu NH and nu OH. So which one will be having a more frequency? So this one, nu HS, this is very important. This comes around 4342 centimeter inverse, and for OH the strong band comes at 3350 to 3200, and then the next priority will be 3300, that is CH, and next NH will comes around 3000 to 2800, and this comes around 2324 centimeter inverse. This for cyanide, this is the free, this is the like for cyanide, if you take cyanide, in that cyanide we will see this this absorption band, and this comes under 1800 to 1900, like that. Okay, so among all these, so new HH stretching frequency is greater than remaining things. So here next we have energy level calculation. So EV equals to nu plus 1 by 2 nu bar centimeter inverse. Okay, so this is the principle to calculate the energy levels, and when V equals to 0, that time it will be 1 by 2 nu bar centimeter inverse. So this is called as 0 point energy. Okay, when V equals to 1, that time it will be 3 by 2. When V equals to 2, that time it will be 5 by 2 nu centimeter inverse. So here we have to remember few points. It's very important. So this is the energy vibrational energy level diagram for a diatomic molecule. Vibration energy level diagram for diatomic molecule which is undergoing SHM, simple harmonic moment. So here the space between the two energy levels will be same here. Okay, so this is V equals to 0, V equals to 1, V equals to 2, this is 3, and this is 4. As we can see in the diagram, the space between two energy levels are same. Okay, the energy level, this point is very important. The space between these two energy level is a half of the transitions, like wait. So we can say that the this energy gap will be the, like, what I'm trying to say that okay, the energy between two vibration levels will be the half of the 0 point energy, half of the 0 point energy. So this point is important. So let's take V equals to 1 and 2. So when V equals to 1, that time energy is this one, 3 by 2, and when V equals to 2, that time energy equals to 5 by 2. So 5 by 2 minus 3 by 2, so this will be 1. Okay, so what is the 0 point energy? Is 0.5. so 1 means it is a half of 0.5. so the energy difference between any two energy level will be the half of the 0 point energy. So 0 point energy is 0.5. so here we have answer 1, so 50% of this one will be the 0.5. okay, so there are two we have what to say, classical mechanics and quantum mechanics. So according to the classical mechanics, the 0 point energy is equals to 0. But according to the quantum mechanics, the molecule, even at 0 degree Kelvin also, it shows some vibrations, and in this case the 0 point energy cannot be 0. okay, so in this from here you have to remember this energy level calculation. The problems will be asked on this energy level calculation, and the gap is same, and the energy difference between any two vibration level is a half of the 0 point energy. And in the classical mechanics, 0 point energy is 0. In quantum mechanics, 0 point energy is not equals to 0. So these are the point you have to remember. So this kind of problems will be asked in exam. So these are the simple and easy. And the question is, consider the diatomic molecule lithium H to be an enharmonic oscillator. Find out the fundamental vibration band, first overtone, second overtone. So here we have a selection rules. Delta nu equals to plus or minus 1, plus or minus 2, and plus or minus 3. So this is for the fundamental vibration, this is for first overtone, and this is for second overtone. Okay, always remember the fundamental vibration will be the high intense one. As we go this side, the intensity will decreases. And one more band we have, that is a Fermi resonance. So this Fermi resonance, it increases the intensity of higher intensity band. So like when we have Fermi resonance, in that case the fundamental band intensity is increases further, and the second overtone intensity decreases. So Fermi resonance increases the high intense band further more, and it decreases the less intense band. Means like Fermi resonance can decrease the intensity of this first overtone and second overtone, and it can increase the intensity of fundamental band. Okay, so I am not going here, like we have one principle. I am not going how it's coming, that I am not explaining. So you just remember this one: En plus 1 minus E naught equals to We minus 1 plus N to Wxc. Okay, if n equals to 0, then this will be a We minus 1 plus 0, this will be 2Wxc. So this is for fundamental vibration. So we can write this one as a W minus 2Wxc. Okay, so when n equals to 1, in that case this will be W 1 plus 1 to Wxc, and this will be W minus 4 Wxc. So this is from E2 minus to E1. So this is E0 to E1, and this is the E2 to E1. Okay, so when it is from the E3 to E2, so that time it will be We minus 6We and Xc. So when they are asking for fundamental band, so that time we have to take this one. So here we have W value, and here we have Xc, means enharmonicity constant. So just substitute these values: 1405 minus 7 centimeter inverse minus 2 into 1405 into 0.0165. So you'll get answer. Okay, so this kind of questions will be asked in the exam. And another thing is, we have to remember this Morse curve also. So the Morse curve is the plot between energy and interplanar distance. And this will be like this, and this explains the potential energy, and the difference between this and this is called as the dissociation energy. Okay, so what this Morse curve shows? It shows that enharmonic extensions, and compressions, of a diatomic molecule. So just remember these 4 points. So next we have isotopic effect on vibrational level. So here we can take, like we know that nu equals to 1 by 2 pi root k by nu. So here nu is inversely proportional to reduced mass. So as isotopes are if isotopic mass is increasing, the stretching frequency decreases. Okay, so when we have imagine that this is for HCl, this is for HCl, and now this is for DCl. Okay, because if we see the reduced mass nu equals to m1 m2 by m1 plus m2. For HCl this will be 1 into 35 by, imagine that this is a 35, this is also 35. Okay, now here 1 plus 35, so this will be 35 by 36. And similarly the reduced mass for DCl equals to 2 into 35 by 2 plus 35, so this will be 70 by 37. And then so now here we can see that the reduced mass of DCl is greater than HCl. So for DCl it's 1.89, for HCl it's 0.97. So because of that, the we can say the different spectral lines here. Okay, and this is very important while calculating the formulas. It is very important. So while doing problems on this isotopic substitution, these formulas are very important. So then we'll see for HCl 35 versus HCl 37. Okay, so here if we see this one, if we calculate the reduced mass for HCl 35, so this is coming like 35 by 36, this is coming around 0.97. So when we are calculating for HCl 37, that time this will be a 1 into 37 by 1 plus 37, so this will be 38 by 37 by 38, and this will come out like 0.72, and this is also 0.972. And here we can see that there is not much difference. Like we can say that there is no difference between the reduced mass of new HCl 35 and HCl 37. Here we are keeping a hydrogen isotope as a constant, but here we are changing the isotope of chlorine. Okay, one time we have 35 and another time we have 37. In that case there is no change in the spectral lines, this will be like this only. Okay, but for HCl and HBr, for HCl and DCl, there will be change. Similarly we can also write for HBr and DBr also, or C6H6, C6Br6 also, and these two, and HCl and HBr, so DBr, DCl. Okay, so the problems will be asked from these three topics. So now we'll solve one question. So here we have the rotational constant and vibrational fundamental vibration frequency of a HBr are 10 centimeters and 2000 centimeter inverse. The corresponding values for the DBr. So we know that the rotational constant is inversely proportional to the moment of inertia. Okay, now the moment of inertia equals to nu r square. Okay, so the nu, we know that nu equals to m1 m2 by m1 plus m2. So for HBr, how much it will be? So HBr will take this is a 79 isotope. Okay, this will be 1 plus 79, sorry, 1 into 79 by 1 plus 79. So this comes out to be almost equals to 1. And for new DBr, 2 into 79 by 2 plus 79. So this comes close to 2. And here see the difference for new HBr and for new DBr. It means the mass is almost double here. From here to here mass is double, here 1, here it is 2. So when mass is getting double, the moment of inertia also should get double, right? Because moment of inertia and reduced mass are directly proportional. Okay, now you come here, the rotational constant is inversely proportional to the moment of inertia, right? So now here moment of inertia is double because reduced mass also double. From HBr, I am talking about HBr to DBr. From HBr to DBr, the reduced mass is double. That means the moment of inertia also double. And here the rotational constant is inversely proportional. That's why this has to be decreased by 2. So new HBr to new DBr. So moment of the reduced mass increased, means reduced mass became double. Then moment of inertia also it should become double. Now the rotational constant, this should become by 2. Then it should be 0.5. Okay, this way you can remember. And for HBr, what is the rotational constant they has given? 10 centimeters. So 10 by 2 equals to 5 centimeters. So this is the rotational constant for DBr. So DBr rotational constant is 5 centimeter inverse. So another thing, simply you can remember that we know that B is inversely proportional to I and I is directly proportional to nu. Okay, so the mass of DBr is greater than the HBr, right? So since the moment of inertia is directly proportional to nu, moment of inertia is inversely proportional to rotational constant, the rotational constant of HBr should be less, so DBr should be less than HBr. So this way also you can remember. So this is about the DBr rotational constant. So imagine that they have given they have given HBr rotational constant, and if you want to identify for DBr, so the principle will be new B DBr equals to B HBr by 2. And if you want for B HBr, this will be 2 into B DBr. Okay, so this is for the rotational constant. So next we'll go for the vibrational constant, and this you can apply for same. Here we can take C6H6, then it will become C6D6, and here we can take HCl, and this will become DCl, like that. Next we'll go for the vibration frequency, because this we have already calculated. Now we'll go for vibration frequency. So the basic principle what we need to remember here is 1 by 2 pi root k by nu. So here nu is inversely proportional to the reduced mass. Okay, so the mass is double from DBr to HBr. So this we know that, right? So now nu, this is for new HCl, sorry HBr. When we are talking about new DBr, so that is root 2, because the reduced mass is double from the HBr to DBr, right? So if you want to identify for new DBr, the principle will be new HBr by root 2. Same what we have done here, same here also. Instead of 2 here it's coming a root 2, because here we have a root. Okay, so this the 2 is coming because from this nu, because nu is not having a root here, but here root is there. Because of that we are getting this one. So this will be 2000 by root 2. So this will be 1.44 root 2. I don't know how much it will be. I don't have calculator. You just calculate for it. Okay, so now If you want to calculate for new HBr, then this will be new dBr into √2. Okay, so just remember these 4 principles, 1 2 3 4, then it will be very easy. And there is another question which is asked in June 2011 in a CSR exam. So they have given this compound CO CN5 H3 minus, this is having a stretching frequency of 1840 centimeter inverse. So what about CO CN5 D3 minus? So what about this? So this is also simple only, like they have given for H, so you have to identify for D, that too this way. D means you have to calculate by this way. This will be 1840 by √2, so you will get answer. Sometimes what they will give, another question they have asked in 2017, that they have given cobalt CO4 H, they have given a four values, 2121, 2062, 2043, 1900, 34. Then they ask for new value of COD. So this is for new of COH. They have asked for new COD, and in this case you can take any value. You can take this value, this value, this value, this, any value. Imagine that you are taking 2121, then it will be, you have to identify first new COD. So what is the principle for COD? So this is the principle. So √2. Any value you can take, you have to do same value, same thing, and you will be getting a answer for that. Okay, so just remember these 4 principles, then it will be very easy. Whatever the question they can ask, you can simply do if you can remember these 4 principles. So for that you have to come from here. Instead of by hearting, if you can remember these things, then it's very easy to, means you will not be forgetting these things.